Hello and welcome back. Today we're going to be continuing with material from lecture 27 in the notes. This concerns calculation of continued fractions. I understand it's been a while since we've been on break, so you may want to go and review my previous lecture where I talk about what a continued fraction is and explain the notation. The later couple of videos in today's lecture will all be covering solutions to problems from the practice test. So I suggest that you give those a shot first before you watch those videos. And likewise, there'll be those solutions spelled out in the PDF notes for today. So assuming that we're cool with what a continued fraction is and how the notation for those works, I want to talk about how to find the continued fraction expansion for a rational number. My condensed notation is the version where I've got a square bracket, I have some integers. A0 is the integer part of this number. A1 is the denominator of the next continued fraction down. A2 here up to AK. So these are all integers. And because we're dealing with a rational number, so here I've got 62 on 23, I know that my continued fraction expansion actually has to terminate. Infinite continued fraction expansions are only for irrational numbers. We can still use this idea to get an approximation for some fraction, right? There's the idea that if we cut off the expansion early, we'll get a continued fraction which is close to this number. And again, that was something that I talked about before break. I want to try to calculate what these integers a0 up to ak are going to be for this fraction 62 on 23 in particular. So my first step is going to be calculating a0, which I know has to be the integer part of this number, right? If I had this in decimal notation, let's say I've got 62 on 23, and my calculator tells me that is 2.695652, some other expansion. My integer part of this number is 2, which means that my A0 in this expansion is going to be 2. But then I need to figure out all the rest of those numbers. I did this previously with finding the continued fraction representation of pi, and that was a bit of a mess with calculating integer part, fractional part, taking reciprocals, and just going to my calculator a number of times. It will be much easier for this rational number because I can just use algebra instead, and I won't need to worry about a calculator. So again, here is the decimal expansion of 62 on 23. Its decimal expansion is repeating, but it's much easier just to say, like, well, 62 on 23 is itself, right? I can convey the same algebraic information in far less amount of typesetting. So my first step I've already explained verbally. The integer part of this number is 2, and the fractional part of this number is 16 on 23. Well, how did I get that? I know that 23 goes into 62 twice, but 3 times would be too many. So I can break this fraction into its mixed fraction form, 2 plus 16 on 23. That would be my first step, just what I have highlighted here. My continued fraction form always requires my numerators to be equal to 1, which I do not have. I have a numerator of 16. So what I'm going to do is, if I end up with a fractional part whose numerator is not 1, I will take the reciprocal of this number, and I can rewrite this form to say my integer part is 2, my fractional part is 1, a numerator of 1, divided by the number 23 on 16. It's not immediately obvious how that gets us what we want, but I've at least got a numerator of 1. I'm supposed to have integers downstairs. Notice that my 23 on 16, I took my reciprocal, so now I've got 23 on 16. That fraction is larger than 1, which is, I know that because I know that 16 on 23 is less than 1. Reciprocals invert that relationship. So I can again ask, how many times does 16 go into 23? And I know it only goes in once. So I can take this term on my denominator, and I can say that 23 on 16 is really the same thing as 1 plus 7 on 16, right? That's just algebra. Everything else here is staying the same. The numerator is the same. This 2 out in the front is the same. That's all great. The only thing I've changed is downstairs. This gets me closer to what I think a continued fraction should look like. I have a 2 plus a numerator 1 and an integer, and then plus another fraction, numerator 7. But I'm supposed to have a numerator of 1 every single time. 7 on 16 is a fraction less than 1, so I'm going to do the exact same trick, right? I'll keep my 2, I'll keep my numerator 1, I'll keep my 1 plus a fraction. But I have rewritten 7 on 16 as a fraction with a numerator 1, denominator 16 on 7. And the steps that I'm using here are going to be the same idea every single step of the way, even though the numbers are getting smaller. And I like that they're getting smaller because that means eventually they're going to have to run out, and I'll be done. So I do this same business. I say that 7 on 16 is just a different way to write 1 divided by 16 sevenths. That's great because it gives me the numerator of a 1 that I'm looking for. How many times does 7 go into 16? It goes into 16 twice with a remainder of 2. So this fraction is really 1 divided by 2 plus 2 sevenths, which is now looking, again, closer to what a continued fraction is supposed to be. But 2 sevenths has a numerator of 2, not 1. I'll need to do this trick again. Say that 2 on 7 is just a more convenient way of writing 1 on 7 halves. These are exactly the same number, just a little bit of algebraic manipulation. How many times does 2 go into 7? 2 goes into 7 3 times, with 1 left over, so I get this expansion. So in my final step, I've only changed this last denominator here. Everything else, all the numbers I determined up to that point, are the same as they were earlier in my equations. At this point, all of my numerators are 1s, and I'm done. My continued fraction representation is to say that 62 on 23 is equal to the integer 2 plus 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3 plus 1/2, which is 1 on 2. So these are going to be the numbers in my continued fraction representation. That tells me in the shorthand version, my continued fraction expansion is 2, and then a semicolon, 1, comma, 1, comma, 3, comma, 2. So that is the whole thing. That's the continued fraction expansion of 62 on 23. Now, there's something that you might have noticed already, that the steps I'm taking and the logic that I'm using are actually the steps of an algorithm that we've already used in this class. So my first step was to say, how many times does 23 go into 62? And it goes in twice with a remainder of 16. Then my next smaller fraction was 16 on 23. So how many times does 16 go in to 23? Then my next smaller fraction was 7 on 16, and so on. At every step of the way, I'm asking, how many times does my previous remainder go into my previous denominator? And that's exactly the same thing that the Euclidean algorithm is doing. That's exactly the same kind of question. It's exactly the same steps I would be using to calculate the GCD of these two numbers. As long as I have my fraction in lowest terms, then I know that the greatest common divisor of my numerator and denominator is going to be 1. So when we do the continued fraction expansion of this number, 62/23, we're really just following the steps of the Euclidean algorithm, which we've been doing since the second week of class. And because of that, we know that the algorithm is eventually going to stop, and that's the reason, that's another reason why rational numbers only have a finite continued fraction expansion. So the big takeaway for this lecture is, if you know the numerator and denominator of some rational number, and you have them in lowest terms, we can very easily calculate the continued fraction expansion of that number using the same old Euclidean algorithm that we've been using for about 2 months now. So it's very handy, I'll say. I'm going to cut off here, and as I said, the remainder of today's lecture bits are going to be solutions to the sample test problems. Please give those an earnest shot before you watch those videos. Those are problem 1, problem 2, and problem 10, and I'll have them marked as such in the playlist. All right, I'll catch you later.